Let's talk about the Markov decision process. So a Markov decision process is just a reinforcement learning problem that satisfies the Markov property. So they have a state that it satisfies the Markov property. And we usually talk about finite MDPs. When a finite MDP means that its members, the states, actions, and rewards, are all finite. And it's a definition of a finite MDP also includes the dynamics that are defined by the state transition probabilities, what we normally call a model. And formally we can show that as the probability of S prime, the next state, and R, the reward, given the current state S and the action A. And we've shown that here as probability of S sub t equals S prime, RT equals R, given that ST minus 1 equals S and AT minus 1 equals A. That's just really defining what it means, what the notation on the left means. And from these probabilities, we can compute anything about the MDP we might need to know, including just the probability of S prime or just the probability of the reward. So let's do an example of a recycling robot as an MDP problem. So its goal is to collect empty soda cans in a cafeteria, and it has an onboard recycling bin where it puts the cans. And the actions that it can take are go home to the home base and recharge its battery, search for cans, or wait for someone to bring it a can. And as an MDP task, we're going to define the states to be low and high for the battery. We're going to say its actions are search, wait, and recharge when it's in the low state. And the actions for when it's in the high state are just going to be search and wait. There's no reason for it to go recharge if it's already in the high state. So we'll just, as a design point, leave that action out here. And it's going to have 3 rewards. -3 if it runs out of charge and somebody has to come rescue it and go recharge it. 0 if it hasn't collected any cans on the current time step. And 1 for each can that it does collect. And we have some other statistical information about the model. R wait is going to be the expected number of cans it receives while waiting during one time step. And our search will be the expected number of cans it finds while searching on a time step. And we also have this probability that it will, if it goes out on a search, if it's at a high charge, it'll stay at a high charge, so that'll be alpha. And 1 minus alpha will be the probability that it goes from high to low. And we have beta is the probability on a search cycle that if it's on low battery, it'll stay on low battery and not run out of charge completely. And from all that, we can build this transition table here showing S and A, the current state in action, and then the next state, S prime, and the probability of achieving that state and the reward associated with that. So for example, on the first line, we have if it's in the high state and it does a search, then the probability that it'll stay in the high state will be alpha. And the reward it will receive will be this R search variable. If it's in the high state and it does a search, the probability it will go to a low state is 1 minus alpha. Okay, we can also look at a graphic form of this table called transition graph, and shows 2 states here, high and low, and the arcs coming out of the states are actions, and the values labeled on the arcs are the probability of taking that arc and the reward received. So for example, if we're in the low state here and we do a search action, there's a probability of beta that will return to the low state with a reward of R search, or a probability of 1 minus beta that will return to the high state, that is, we'll get stranded and rescued and recharged, and we'll get a reward of -3 for that.